Okay, you can hear me well. Welcome everybody. So it's cold today and yesterday we were discussing, we just started multiples methods. So we will just discuss the basic idea of multiples so that if somebody is interested, they can go deeper in this area. It's a very hot topic. So as we discussed earlier, there are many applications of multiples technique that we already discussed. Okay, these applications we have already discussed. Then what are basically these things? On AC side there is a problem, DC side there is a problem with rectifiers. So these things we have already discussed, and we were talking about two separate six pulse converters. Okay, and dy1, dd0 we have already discussed how 30-degree phase shift 6 pulse discussed, like since it is a 12 pulse, so 11 and 13th harmonic will be there. So as you same load. So if why it is not moving? There is some problem here. The problem of circulating current, so that is why we were using interface transformers. This we have already discussed. I think I have some problem, my slides are not moving. Yeah, okay. How to escape? Why it is frozen? It is going for, ये आगे बढ़ता जा रहा है, पीछे नहीं जा रही स्लाइड्स, एस्केप भी नहीं कर रहा है. कुछ बात नहीं, में हम आगे बढ़ते हैं. ओके, हो जाएगा. अच्छा, इसे रीसेट करना पड़ेगा. सर हो जाता है. सर चार्ज नहीं है. चार्ज, हाँ ये चार्जर है इसका. सर हो जाएगा. हैंग हो जाता है. अच्छा, अभी पहले ऑन होने दो, फिर इसके बाद. ये चार्ज में ना इससे ऑन होगा ना. ओ शटिंग डाउन करने लगा था. कोई नहीं, हो जाता है, कोई नहीं, 2 मिनट से. ओके, सो एक मिनट यार, नहीं हैंग हो रहा था तो कैंसिल है. नहीं डिस्कार्ड कर लीजिए, खोल लीजिए, ओपन कर. अच्छा, ठीक, अच्छा इसमें ऐसे ही करके देखना, क्या हो रहा है?
क्लिक नहीं हो रहा, हो गया, ठीक है,
ये क्या हो रहा है? ये इससे तो आगे बढ़ रहा है, बैक नहीं जा रहा है।
ऐसे नहीं है ना? नहीं, टच से तो जा रहा है ये तो।
हाँ, टच से जा रहा है। चलो तो टच से हम यूँ कर लेंगे। हाँ, और क्या, इट्स फाइन। ये
बटन अभी कुछ काम,
हाँ ठीक है, ठीक है, ठीक है, ठीक है, ठीक है, ठीक है, चल बढ़िया।
आ जाए, आ जाए, नहीं आज ही आएगा,
आ गया, आ गया, इसे ठीक है, ठीक है, हम कर लेंगे। थैंक यू। So I think we have already discussed these things. So we were talking about in general minimum phase shift required for cancellation of current harmonics in converters with 6 pulse waveform, 6 pulse. So phi is the minimum phase shift. Okay, so 60 divided by n, n is the number of 6 pulse converters. So if you have two 6 pulse converters, so basically 12 pulses and 60 divided by 2, right? This is what we were discussing because there are two converters. So 30-degree phase shift. So if you are having two converters, like we were having DY1 and DD0, two converters were there. So why we were giving 30-degree phase shift? Because this is the requirement, minimum phase shift is 30-degree phase shift required. So that's why we were giving 30-degree phase shift to cancel 5th and 7th harmonic, right? So this was the advantage of giving the phase shift. So this is what we were doing, that if we have two converters, two 6 pulse converters, so 30-degree phase shift. If we have 3 6 pulse converters, then you see 18 pulses. 18 pulses means minimum you will have 17, right? So below 17, all the harmonics are already removed. If you have 3 6 pulse converters, and how much should be the minimum phase shift? 60 divided by 3, because we are talking about 3, so it means 20-degree phase shift. So if you are having 3 converters, 3 6 pulse converters, so minimum phase shift would be 20 degree to get 18 pulses, so that below 17th all the harmonics are already removed. So this is the advantage of giving the phase shift between the converters, right? So n is equal to 4, so 24, 6 multiplied by 4, 24 pulses, and 60 divided by 4, so 15 degree. So this is how you can calculate for all these things, right? This is also we have already discussed. So if we have one converter, 6 pulse converter, so this is the equation. So you will have 5th, 7th, 11th, 13th, 17th, all those harmonics are there. If you have m converters of 6 pulse, so this is the equation, and you can see this is the amplitude. So if you have 3 converters of 6 pulse, so m is equal to 3, this m is equal to 3, so you have 18k plus minus 1. So 3 6 pulse converter means 18 pulses, right? 18 pulses, and you will be giving 20 degree phase shift, 60 divided by 3, 20 degree, and you will get 18 pulses, and this will give you what harmonics you will get with 3 6 pulse converters connected in parallel with 20 degree phase shift. It will give you 17. So below 17th harmonics are already eliminated. So this is the advantage of giving the phase shift. So that is why in industry, if you say, okay, this is production line and we can have the same kind of production line for all our equipment, so it will generate a lot of problem if you do it in industry. That's why phase shifting is very important, right? So, and this is the amplitude of harmonics you will get with this formula. Many times we use zigzag connection, delta zigzag. This is delta in the primary. In the secondary, you have a zigzag connection. So what are the zigzag advantage which we have already discussed? That there is no core saturation due to DC component. This is the big advantage of zigzag connections. No zero sequence current in delta in the primary side. Otherwise, if you take DY11 or DY1 or other those type of configuration, on the distribution network side, certainly there is no third harmonics or zero sequence harmonics, but they will circulate in the delta primary side of the transformer, which will heat up the transformer basically. Unnecessarily it is heating up the transformer. But if you have a zigzag connection, then there is no zero sequence current even in delta. They are eliminated. So this is the advantage of having zigzag connection. And then we can have any phase shift adjusting the number of turns in secondary. You see here, like for example, here it is 15-degree phase shift. See, this is the output. So this is from primary side, and in the secondary side you can see 15-degree phase shift. So by adjusting the number of turns here and in this winding, small winding, you can change the angle, whatever angle is required, which harmonic you want to eliminate. You can have 7.5 degree or 15 degree or 20.5 degree, whatever you want, or even you can have one zigzag also like this, okay, which will go like this, okay, so that it will give minus 15-degree phase shift in parallel with this. Double zigzag you can put, sometimes they put double zigzag also. Now zigzag, we have, instead of having zigzag in the secondary, we can have polygon connections. So it is the same transformer, it is just how you connect it, like the same transformer, either you can connect in delta or you can connect in star Y connections, right? So it is the same thing here. So instead of opening the windings like this, like a star, you can close them like this. So this is a polygon connection. And here also you can have the same thing, like 15-degree phase shift here. Okay, depending on the number of turns in the primary, here, you can adjust the number of turns. And so the only difference, it is closed at delta, zigzag for higher voltage, polygon for lower voltage. But polygon is also very popular in applications. So you may think that it is difficult to analyze this thing, but it is not very difficult to analyze those transformers. Suppose we analyze this polygon transformer, right? In this polygon transformer, you can see on the primary side you have delta, this winding and this winding and this winding. They are on the same leg of the transformer, and the sum of magnetomotive force should be 0 in that leg. So this is how you can write this equation, right? IA is the current here in this winding multiplied by number of turns. So MMF is there, and this is in the opposite direction. I1M current is NL. So number of turns here. So we are talking about ampere turns, like MMF, ampere turns. NL multiplied by IM, and then here you have I3M current in this winding. And this you can say number of turn NS, because it is small winding, or this is large winding, and this is on primary side. So all these three are on the same leg. So sum of all this MMF should be 0. Okay. Now if you see this triangle, this is VNL here and this is VNS voltage. Sum of these two is this voltage VLS. This is the output voltage. So if we say this is the phi angle, okay, so you can see here if you analyze, this is VNS sine 60, this one, and this is VNS cos 60. So if you calculate tangent of phi, so this voltage divided by this voltage, right? So that we have written later, but what we have done, this voltage divided by sine of C. See, this is the trigonometrical function you already know, right? This VNL, this is in front of this. So sine, this VNS divided by sine 60 minus phi, this divided by this angle, this divided by this angle. So this is how this equation, trigonometric function, has been written, and you can find the voltage VNL, VNS, those things, and then you can write tangent phi. The objective is to find the angle phi. So how you will adjust the angle phi? So that depends on the requirement, what kind of load is there, what harmonics are generated. So depending on, you can do the calculation which phase difference between the transformer will be helpful to cancel certain harmonics. Accordingly, you calculate phi, and phi you can adjust by the transformation ratio. Okay, so then we have analyzed it here, I1M, so there's some problem. If you see this branch here, I1M is there, and this is I3M, so you can calculate I1. I1 will be I1M minus I3M. Same way you can calculate I2 and I3 using Kirchhoff's current law, and it is easy to write this equation. See, current I1 is equal to I1M minus I3M. Same way I2, I2M minus IM. And then finally you can resolve this equation, and then you see this equation we have already seen. So finally you can calculate IA, IC, and then I1N. This is the current on the primary side of the transformer, IA minus IC. So it is just to give you, I can analyze this transformer. So whenever you have time, you can look into it and try to solve this thing. And then you see, this is the equation you can get. Now coming to other topologies, there's so much work is going on in this direction for last more than 20 years. Okay, so it is a very hot topic, and people are every year. So here I am not giving you more complex topologies and of multiples which has already been developed. Here I am just giving you the basic idea to so that you might, perhaps some of you might be interested in working in this area. So you see here we have 3 converters connected in series, 3 6-pulse converters. 3 6-pulse converter means how much phase shift? 60 divided by 3, so 20-degree phase shift between the 3. And you have 3, so 18 pulses will be generated. So as you can see here in this line, see it is already so much smooth. If you take only one converter, it will pollute a lot, but now because of the phase shifting, So this is delta, delta, 0 degree here, then this is plus 20 degree and this is minus 20 degree. So this is how you can do the phase shifting using polygon. So delta, delta, double polygon. So delta on the primary side, secondary side another delta, and 2 polygons are there which will give you 18 pulse. So up to 17th harmonic they are already eliminated. So minimum harmonic is 17th in this. So 5, 7, 11, 13 they are already eliminated. And it does not need the interphasing transformer. Now if you see this delta hexagon, primary side delta, and this is the hexagon. So you can have, this is the output 1, 3, 5, see they are connected here, 7, 9, 11, all these output terminals they are connected here, okay, and this 2, 4, 6, 8 they are connected at this point. Okay, so this is full wave midpoint converter, and if you see between 1 and 2, it is 30 degree phase shift because there are how many? 12. 360 divided by 12, so 30 degree phase shift, right? So it is having 30 degree phase shift. But this, so there is already a US patent. This is nothing new. This is old, maybe 20-year-old patent, more than 20-year-old patent. But you can use this hexagon as auto transformer also. Then you don't need this. Okay, so you can have input here 1, 9, 5. What will happen? 1, 30, 30, 30, 30, 120 degree, right? So you can have input here, you can have input here, and you can have input here, and everywhere else you can have the output. So see, this is the auto transformer. That is also very popular, that type of. So what actually, if you see the multipulse techniques with double winding transformer, and you have option multipulse technique with auto transformers. So what is the advantage of double winding transformer? That it has DC isolation between input and output, right? And what is disadvantage? You have doubling the kVA and other parts. Like if we say, okay, I have a double winding transformer and it is a 10 kVA capacity. So input winding is 10 kVA and output winding also 10 kVA because power has to be transferred. So it is basically you are doubling the kVA, right? So it will increase the size, terminals, boxes, and it will increase the cost and it will decrease the efficiency because more winding wire and more losses are there. But if you have auto transformers, then what is the advantage? For particular phase shifting, design is simpler, reduced kVA. So if we say 10 kVA, it means it is 10 kVA, it is not 20 kVA, right? It is auto transformer, same windings are used. For example, with auto polygon, 30% of double winding transformer, see, this is the advantage. If you have double winding transformer and with like delta polygon or something, or if you have auto polygon, so you will say, so it will be a 30% of double winding transformer. So that much cost you can save. Cost much reduced. This is more compact because now it will be smaller, right, with higher efficiency. And but the disadvantage, there is no DC isolation because same winding you are using for input and output, right? So this is an example of auto connected polygon. Till now we have seen delta polygon or something like this. So that was double winding transformer. But if you want to see auto polygon transformer, so you see this is the input here and this is another input here V2, and this is another input V3. So 3 input, 3 phase supply, and then you can have output I2, I1, I2 and I3. So 3 output. So you can get particular phase shifting with the same transformer. You don't need double winding transformer. You are getting the phase shifting with this. So how to get 5, that we have already seen. You can see this is the phase shifting. This is the, here you have the input and here you have the output. So between input and output, 5 angle phase shift is given, phase shift angle. And it is easy to analyze because you see this winding and this winding, they are on the same leg. Okay, so you can write total MMF on the same leg should be 0. So this is what equation IA NL, if this is NL, IA NL, this is MMF, ampere turn of this winding, and this winding, I think this is NS, small winding, number of turns is small, multiplied by I3 plus IB. So the total MMF you can, because this is in this direction, this is in this direction, so you can write, and then you can write NL you can bring here, and N is equal to NL divided by NS. So you can write this equation for current IA, for this current. Okay. Same way you can write for IB and IC, same type of equation. Then you can see this is IB here. So if you put here, then there is IC here, this equation you can put here, and finally you can find out IA current like this, IC current like this. And I in is equal to I1 minus IC plus IA. If you see this diagram, I in current is here, this is I1 minus IC here, and this is IA. So this is how you can write all those equations. And then you can calculate the phase angle and those things. Another type of transformer is fork connection. This is a fork connection. This is auto fork connection. So you have the input here. You have input 1. Oh, this is I2. This is I1. This is input 1, 2, and 3, I3. These are the 3 input, and output is here. See, this is output, and this is output. So between input and output, you have phase shifting 5 degree. Okay, but according to some reviewers, it is less efficient in comparison to auto polygon for same phase shift. KVA is higher than polygon. This is what other people give comments about the transformer. Then we have differential delta. Differential delta is very popular. Okay, so you can see these windings and these windings, they are on the same leg, and this winding and these two winding, they are on the same leg. Okay, so if you write MMF equation, this is IB current multiplied by NL, suppose we call it IB NL, and here this is I1 current in this winding, I1 NS, if we say NS number of turns here, I1 NS, but they are in opposite direction, so minus, this is I4 current, I4 NS. So this is what MMF equation you can write. What is the advantage? See the equation. This IB current here, this is proportional to the difference between I1 and I4, differential of these two currents. So it means current IB will be very small in this. So this is IB current is not very large, this is very small because it is the differential between current I1 and I4 because they are on the same leg. So this transformer is very compact, And phase shifting you can get here, see, plus 15 degree for this it has been, and minus 15 degree. So you can have, so you see these are the inputs. So three phase input. Okay, so here you have three phase input like this. Okay, and then you have output, all those I1, I2, I3, they are going to this 1 6 pulse converter, and I4, I5 and I6, this is going to another 6 pulse converter with minus 15 degree phase shift. So total phase shift is 30 degree phase shift you have between the two. Between this and this you have 30 degree phase shift, and you can connect these two in parallel. So this is what plus is connected to plus, but there is an interphasing transformer between the two, and minus is connected to minus, and there is an interphasing, and this is the output you can connect here. So if you see, this is what we were saying, that for example I6, where is I6? I6 minus I3, that should be proportional to IA, right? Because this and this, they are on the same leg. So I3 minus I6. This is I3 waveform, and this is I6 waveform. Difference of these two, you see, it is going, so see, IA is so small, so it is very compact, very big advantage. Then we have another type of differential delta, right, so that you can connect 3 converters in parallel, same way, and the windings, these, they are on the same leg. So if you are having 3 converters, the minimum phase shifting is required 20 degree, 60 divided by 3, 20 degree. But here we have 40 degree phase shift, because 20 degree is the minimum. So some conceptors of the transformer, they said, okay, I can take 40 degree phase shift. So he has taken 40 degree, and this is how he is able to get 18 pulses here. This is another differential fork. Okay, so many different transformer, and this is a hybrid delta, this is auto transformer, and this is another connection. That's why the conceptor is saying, okay, we have the advantage of double winding transformer also, and here we have auto transformer also. So now using these auto transformers or those things, we can have the phase staggering like this. See? Can you see how much money you can save in this thing? Because it is the same thing, like you are using dy1 and dd0. Here you don't have to have any transformer. Directly you are connecting. So 0 degree phase shift is there, right? And here you can have auto polygon with 30 degree phase shift. You can adjust the winding here and here, and you can get 30 degree phase shift. And this is on the top of this is auto transformer, much cheaper. So the cost of this will be 25% of the original which we studied, dy1, dd0, the cost of that setup and cost of this setup. This will be 25% of that cost. So this is what engineer has to see, how they can save the money and how they can have good performance. Now this is another double winding. This is although showing double winding, but you can have auto polygon also. Okay, so if you have auto polygon, see the third 6 pulse rectifier, it is directly connected to the supply, 0 degree phase shift, because you are having 3 converters, so 20 degree phase shift, 20 degree plus 20 degree and minus 20 degree. So this will give you plus 20 degree, this will give you minus 20 degree, and if you are directly connecting to the rectifier, so this is giving you the very cheap option for 18 pulses. Basically you will get 18 pulses, right? 17 up to 17th harmonic already limited. Then this is also popular sometime, that you have for identical loads, and directly you can connect one 6 pulse converter, and since you have 4 converters, so 60 divided by 4, 15 degree phase shift. So each has, so this is minus 15, this is 0, this is plus 15, and this is plus 30. So this is how you can have 15 degree phase shift between the converters, and finally it will give you 24 pulses here. So up till 23rd harmonic they are already eliminated. So minimum harmonic is 23rd harmonic. So you can see it will be very good. But sometime what happens that some converter is not working due to some reason, then the performance will not be that good in this, right? We are assuming that all the loads are there all the time. Suppose this is working and this is working, then it is fine, 30 degree phase shift. So even if these two are gone, you still have 30 degree phase shift, and you will have 12 pulse performance. But somehow if these two are gone, then it may not give very good performance, because 2 converters and 15 degree phase shift, that will not give very good performance. So there are some advantages, disadvantages, but you can save lot of money in this thing. And then there are other configuration also, but I will. So we have to move on to our the other topic. Active shunt active power filters. Okay. So what we will discuss in this presentation, what are the requirements and applications of shunt active power filters, configurations of shunt active power filters, control of shunt active power filters, sharing of responsibility for harmonic distortion and power quality. So generally we don't find this topic anywhere, but few years back I did a very interesting project in collaboration with Hydro-Quebec, sharing of responsibility. Otherwise it is difficult to do this thing. And then numerical problems and references. So if you see the requirements and applications of shunt active power filters, these are current based power quality problems and in distribution system for which we use shunt active filters. So what are the problems? Problems is that RMS supply current may be high, there might be some low system efficiency because of the increased losses, poor power factor, poor utilization of distribution system, heating of components of distribution system because of the different harmonics, right? And then derating of distribution system. Suppose transformer has lot of harmonics, so you have to derate the transformer, and sometimes you can have only the 50% of capacity. Distortion in voltage waveforms at PCC, interference to communication system, disturbance to nearby consumers. So these problems may arise in a distribution system, and these are current based problems. So for these problems we can use shunt active power filters to improve the power factor, for voltage regulation, For unbalanced current, if there is excessive neutral current, your shunt active power filter will work fine, and then harmonics. So solution is the shunt active power filters for all these problems. So it is nothing new, it is a very mature technology, because you know the 40 years ago this Akagi developed one control technique, instantaneous reactive power theory. So it means that time also they were using, but with the development of IGBT technology and those things, it has picked up so much. So now mature technology for providing harmonic current, compensation of reactive power, load balancing, neutral current, okay. And shunt active power filters, they are also used to regulate terminal voltage, to suppress voltage flicker, to improve voltage balance in three-phase system. So there are so many applications, and so much development has taken place in this technology with varying configuration, advanced control studies, so many. A new PhD student will come, he will develop his own control technique, right? He will modify existing or something, and then, so many control techniques, strategies are being developed, and then solid state devices, so much development has taken place, like gallium nitride, silicon carbide, and so much development is taking place in solid state devices. Improved sensor technology, Hall effect, current and voltage sensor, and then there is a development in microelectronics revolution, microcontrollers and DSPs. So much new products are coming with very good performance and those things. So lot of development is going on with the technology, which is helping to give a push to this active shunt power filters to improve the power quality on distribution systems. If you see the classification of shunt active power filters, you can see, you can classify based on converter type, based on the topology, and based on the number of phases, right? If converter type, you have current source converters, right? And you have voltage source converters. You have, for the topology, you have half bridge topology, you have full bridge topology. Number of phases, you can have single phase 2-wire system, or you can have 3-phase 3-wire system, or you can have 3-phase 4-wire system. Okay, so based on that, the topology will be changing. So if you see the converter based classification, so if you have a current FET type shunt active filter, so you can see current FET, so your IGBT is here, and you have to put a diode in the series to counter the inverse voltage, right? And on the DC link, you have an inductor, okay? So current source inverters use a constant DC current input to produce a variable AC current output. It uses large inductor for energy storage here, and to keep current constant here, IDC. Large inductor may be heavy, noisy, and may cost more. So current source inverters are better for high torque applications at low speeds. So this is the application basically for current FET type filters, and offer a more stable current output. Now voltage FET type shunt active filter, you have IGBT configuration like this, you have diode in parallel, and then you have a capacitor on the DC link, right? So voltage source inverter use a constant DC voltage here input to produce a variable AC voltage. DC link capacitor to maintain constant voltage here. Less losses, high efficiency, smaller size, less noisy, less costly in comparison to current FET type. But current FET type are used for large system and those as we have seen low speed, high torque drive. So this is more popular than voltage FET type. They are more popular than current FET type. That is number of applications. So basically it depends what application you are using, right? Topology based classification. See, half bridge topology. So you have a half bridge here, VSC based, single phase. This is single phase, shunt active filter. So this is how coupling inductor you are connecting here, and here you have two capacitors and midpoint you have connected here. So this is the half bridge topology. Basically, to save some money, it will cost cheaper in comparison to this topology, full bridge topology, because you have another set of IGBTs here and you have one capacitor. So here you are connecting to, because this is again a single phase. Okay, so this is how you can have full bridge topology. Supply system based classification, again the same thing. Suppose this is a current source inverter. You can see the diode connected in series with IGBTs, and two wire shunt active filter. So it is connected here, and you have an inductor on the DC link. Two wire shunt APF voltage source converter. Again we have seen these things. Okay, so this is full bridge type, basically voltage source converter. Three phase, three wire shunt APF. So three phase, this is three phase, three wire. We don't have neutral here, and so we have three phase full converter here, and then on DC link you have a converter, and these are the coupling filters. So this is what the topology. You have three phase, three wire shunt APF with VSC. Three phase, four wire. So now you have neutral also here. You have three phase with neutral current. So sometimes we can use two capacitors, and midpoint you can connect it here, the neutral. Though this is cheaper for three phase, four wire topology, because neutral is connected to capacitor midpoint. Sometimes triple harmonics may flow through the capacitors. A may require large capacitor sizes. So these sizes may be large because zero sequence current may flow through those capacitors, and they may heat up the capacitor. So you may require large capacitor size. So that's why if you use the fourth pole to connect the neutral, so it may look costlier, but it gives very good performance. And then you have three H bridge, four wire shunt APF. You see, this is H bridge, three H bridges, and you have a neutral here, and so each phase harmonics are compensated independently by a separate H bridge. Like, see, this is for phase A, this is for phase B, and this is for phase C. For large nonlinear load applications, number of components increase, hence less efficient, because losses, if you are using more components, so losses will be more, and it may be less reliable also. So if you see the principle of operation of this active filters, so main objective, as we have already seen, that current based power quality problem, harmonics, reactive power, unbalanced load like unbalanced current, neutral current, fluctuations. It results in sinusoidal balanced currents in the supply with its DC bus voltage regulation. In general, shunt APF has a voltage source converter connected to DC bus and AC side. Okay, and VSC uses PWM control. Therefore, it requires small ripple filters to mitigate switching ripples. It requires Hall effect voltage and current sensor for feedback signals. Digital signal processing is required. Okay, to implement required control algorithm to generate gating signals, right? VSC is normally controlled in PWM. This we have done. So other requirement, DC bus capacitor you need AC interacting inductors, injection and isolation, small passive filters. Time domain control, so there are time domain control algorithms, there are frequency domain, so much work, so many algorithms have been developed by a new researcher will come, he has to develop a new control technique to finish the PhDs and get some simulation results and implementation results. So much work is going on in this direction. Okay, so many time domain control algorithms, unit template technique, controller power balance, so see so many algorithms, instantaneous reactive power theory, synchronous reference frame theory. So there is no limit. And then still you can have those algorithms. Now if you see the frequency domain control algorithm, there are so many frequency control domain control algorithm also. So you see, if you see the working of shunt active filter, so this is you have three-phase nonlinear load. And you have voltage source converter in shunt, connected in shunt with this. This is the supply source, these are the impedance of phase A, phase B, phase C line. And then, because you know this is three-phase diode, so what you may have perhaps this kind of suppose you have this kind of current, okay. So if you don't have this shunt active filter, this current will directly go to the three-phase source. So what is your objective? Your objective is to have sinusoidal source current. This is the objective, right? So sinusoidal current means you should have sinusoidal current like this here, supplied by the source. Okay, so what is the difference between the two, right? So suppose you have this sinusoidal current of the source, but on the load you have this kind of, so the difference between the two, see, this is the difference between the two. So basically it will be something like this. Okay, something like this. You have to have, so this is the part of current which has to come through this shunt active filter to make the source current sinusoidal. Okay, so there are so many algorithms. The simplest one and which works very good also, this is the unit template or PI controller based control algorithm. So what you do is that you measure the supply voltages and then using VSA, VSB, VSC, you estimate the voltage amplitude. Okay, so suppose you write VA is equal to Vm sine omega t, VB is equal to Vm sine omega t minus 120 degree, and Vc is equal to Vm sine. So this is what is actually you have, right? These voltages. Supposing they are sinusoidal. So this is the thing. So we are assuming that those are sinusoidal voltages in phase A, B, C are provided. So we can write this equation. VSP, okay, so VSP. So what we do is that we measure these voltages divided by Vm, this divided by Vm, this divided by Vm. So these are cancelled out. So you have sine omega t minus 120, sine omega t plus 120. So this is what we are getting USA, USB, USC. You are dividing these voltages by the amplitude of the voltage, estimated amplitude of the voltage, which will give you sin omega t minus 120, sin omega t plus 120. So this is what the unit vector you are having, unit template. Now you measure the DC link voltage, and this is the desired DC link voltage, and then using the PI controller you estimate the amplitude of the supply current, and that is the amplitude is multiplied by these 3 unit vectors, and finally you are getting the reference for source phase A voltage current, reference for source current for phase B, reference for source current of phase C. Okay, so this is how, you see, this is what we are doing using this one. Then there is another algorithm which we developed many years ago, but this is what you have to see when you are, what is actually classical theory. What happens is that either you do voltage regulation theoretically, either you voltage regulation or power factor correction. The two cannot be 100% good. So there is a trade-off between the two. If you are doing the voltage regulation, then you are required to give some leading current, then only you can do the voltage regulation. So see, here you see, suppose this is the load voltage and this is the line current. So drop in the resistance and drop in the reactance source current. So this will give you drop. So basically this is the source voltage. So you see, this is the voltage regulation is not there. This is without voltage, without shunt active power filter, your voltage regulation, this is the load voltage is much lesser than the source voltage. So what we are doing using the shunt active filter, see, this is the load voltage, this is the load current. Okay, so we give this current by the compensator, your shunt active filter. So shunt active current plus load current, it will become the source current like this. So source current parallel of this, you have drop in the resistance, perpendicular to this drop in the reactance. So you are getting the source voltage. So it means this, if you draw the circle, see, the source voltage and load voltage, they are same amplitude, and this is what you are getting the voltage regulation. But at the same time, your power factor, if you see the angle between Vs and Is, power factor is leading, not unity power factor. Okay, so this is the trade-off. You have to see how much power factor improvement you want, how much voltage regulation you want, and accordingly you can put the weight. So this is what we can do here. We are measuring VDC. This is the reference of DC link voltage, and we estimate average DC bus voltage amplitude of in phase component of the reference. So this is what is this? This is the estimate of the amplitude of in phase component. See, D, in phase component of the source voltage. And you are measuring 3 voltages, VSA, VSB, VSC, and you calculate the amplitude like we have done earlier also, and you calculate in phase unit current vector, these. Then you multiply this current by this will give you the reference in phase source current references. But if you calculate the quadrature, in quadrature of this, and you multiply with this, because you have this amplitude of the source voltage estimated, and this is the required one, and it will computation of the amplitude of the quadrature component of reference supply current using. So this is the quadrature amplitude of the quadrature current multiplied by the quadrature current vector, which will give you the reference of the source quadrature voltage current for phase A, phase B, phase C, and these two together it will give you the reference of the source current. So this is what is the basic thing. Now there are so many algorithms. Okay, so everybody saying, oh, this is good, this is good. So whatever works is good. Okay, so this is instantaneous reactive power theory. So many people are using it since 1983 when it was developed by Professor Akagi. Okay, so what is there? You measure VSA, VSB, VSC. You do the Clark's transformation, ABC to alpha beta transformation, V alpha, V beta. You measure 3 load currents, ABC to alpha beta transformation, I alpha, I beta. And then you calculate using this equation. So this is what the work of Professor Akagi. He calculated load power, active power and reactive power using this equation, and then PL, QL, and finally instantaneous active power and instantaneous reactive power by adding some losses here and some voltage regulation thing, and finally using this equation you are calculating I alpha reference, I beta reference, and then you can do inverse Clark's transformation alpha beta to ABC, and you are getting 3 reference source current. So this is what is the basic idea of instantaneous reactive power theory. Then there is another very interesting synchronous reference frame theory was developed. This is still older. This was perhaps developed in 70s. Okay, so but application is still there, right? So what is there? You are having load currents, and you are having ABC to basically Park's transformation, ABC to DQ0, ILD, ILQ, and then you are measuring VSA, VSB, VSC, and using 3-phase lock loop. In MATLAB you will find this block. Okay, so to calculate cos theta sin theta term. So using this cos theta sin theta term, you can use it here to calculate ILD, ILQ, and then low pass filter, DC component of ID current and DC component of IQ current, and then you are adding some current losses, so ID reference, and here you are adding for voltage regulation Q quadrature current, IQ reference, and then DQ to ABC transformation, and you are calculating this reference source current. So basically, as you have seen, the objective is to calculate the reference of the source current. There was some algorithm I saw, they calculate reference of the compensating currents. But that is more involving, more time consuming, so they are generally not preferred. So instead of calculating the reference of compensating current, we calculate reference of the supply current. That gives better performance. So if you compare these two popular things, everything is working fine. So one student will work on this SRF, another will work on instantaneous reactive theory, PQ theory we call it, and everybody claimed that they are working fine. So everything is working fine. Okay, but what is theoretically you can say?
Sometimes I feel that these two theories are sufficient for ourselves.
Yeah, so you see, synchronous reference frame theory is more robust theoretically, for saying theoretically, for shunt active filter, especially under unbalanced conditions. If the supply voltage is unbalanced, then, right? While the instantaneous reactive power theory is computationally simpler, but performs poorly with unbalanced supply voltage. Okay, this is what actually people say. SRF uses transformation paths and inverse transformation, which increases its complexity whereas instantaneous reactive power theory avoids this but requires balanced and sinusoidal source voltage for effective performance. But now so many variants are coming, so researchers, they try to modify SRF also and instantaneous reactive power theory, and they say, okay, it's working fine. And most of the cases, really it works fine, nothing to worry about. Now, if you see the performance of 3-wire APF active power filter at non-linear load for harmonic elimination. See, this is the supply voltage, this is the supply current, load current for phase A, load current for phase B, load current for phase C. Can you see it? And these are the active filter currents for phase A, phase B and phase C. And this is the DC link voltage. So see, if you see the load, phase B load, phase A load, phase C load, and if you see the compensator currents here for phase A, for phase B and for C, so it means they are compensating for this non-linear load so that the source current is sinusoidal constant. So this is what actually basically, as I discussed in the beginning, that this is what is the objective, to have the sinusoidal source current even if whatever load is there, so your compensator should be able to do it. This is what it is doing now, right? Now in this period you can see load current, load at phase A is disconnected. So you have currents in phase B, load B and load C. So still the current which is coming out from the source, it is reduced because 1/3 load is reduced. So still it is sinusoidal and harmonic free, right? This is the what we are, and you can see the 3 phases of the same shunt filter, they are providing, it is providing different current to compensate this basically, because there is no current, so it is almost sinusoidal here to compensate it. So this is, and if you see this is the voltage of phase A, this is the source current of phase A, and this is the load current of phase A. So if you see the THD in voltage of phase A, it is 5.96 THD. And source current THD is 1.6, much less than 5%. And load current THD, it is more than 23% THD. So it means your active shunt active filter is working fine and harmonics are being removed. If you have 4-wire APF with neutral, okay, so here you can see this is the source voltage, source current, and this is the current in the neutral wire of the source. This is load current in phase A, load current in phase B, load current in phase C, and this is the neutral load current, this one. And these are shunt filter current phase A, phase B, phase C. So here you can see this is the load for phase A, B, C, and these are the shunt active filter current. So they are working in such a fashion that your source current is perfectly sinusoidal and of the constant amplitude. But now phase A load is disconnected. So you see the compensator current for phase A, B and C, they are still function in such a way that the source current, although is reduced because this load A is reduced, so still it is sinusoidal. Okay, and at the same time you should see the neutral current for load A, for line neutral line neutral current. Okay, and but here you see the source current, source neutral current, which is 0. It means load neutral current is there, but it is not appearing towards the source. Okay, because this current has been compensated by this. Now let us see, this is again the THD and those things. Oh, these are the experimental results for APF under, so this is VSA phase A source voltage, and this is oh, I think the student has put the same source current, although it is written ISA, ISB, ISC, but still you see, and then this is the source voltage, and this is the load current, right, load current, and this is the source voltage, and this is the shunt compensator current. Okay, and that's why your source current is sinusoidal, and this is to show the THD harmonic spectra of ISA. THD here is 3.9%, and this is load current THD, 26% THD, and this is VSA, 6.4 THD in VSA. Dynamic performance of APF during, I think we should hurry up, there are so many results here. Just to, basically the same thing, like phase A load is removed, here it was, compensator was working fine, so that is why the source current is sinusoidal, and here load phase current is reduced, but it is equally distributed. So load of phase A is removed, but so it is becomes unbalanced load, but it is equally distributed in all the three phases towards the source. This is what actually you see, it is equally distributed in all the source current. This is what basically the objective is. Then there are some other thing, implementation. I think this is, it is just to show here, see, this is the source neutral current, almost 0, while the load neutral current, you see, you have the, because your load is phase A, phase B, phase C is like this. Okay, so this is the load neutral current, but your compensator shunt active filter is generating load current in such a way, you see, it is opposite of this, it is to cancel out this. So that's why source neutral current is null, because load neutral current is cancelled by the shunt active neutral current. Yeah, this is what actually I wanted to, although this is not that interesting for other applications, but sharing of responsibility for harmonic distortion and power quality. So this is what we did project, although I did it 20 years ago, I engaged my postdoc and PhD student in this, and there was one researcher at IREC. IREC is the Research Institute of Hydro-Quebec, It's a very big, 500 researchers or PhDs are working in that institute. So there was one very good researcher, Professor K. Srinivasan. He was working on this problem, that your PCC voltage is all polluted, right? A lot of distortion in the voltage. And all the clients connected to PCC, they are also polluting the network. So how will you decide who has done how much pollution? This is a big question. Because another client may say, no, this is not my pollution, I have not done this. Another client may say, this is not my responsibility. How to share the responsibility of harmonic distortion and power quality. So he did theoretical work, but he did not know how to implement it. So that's why he came to me, okay, this is my theory, how we will implement it. So that's why we did this project, okay, to help him out. So, oh, okay. Okay, tea break, good. that there are many clients, non-linear loads are there, so PCC voltage is also distorted and all currents are distorted. How to define the responsibility of each one without penalizing anyone unreasonably. How to find the attribution to harmonic distortion of each one. So how to separate utility and customer harmonic contributions at the point of common coupling, and how the customer should filter out only that portion of harmonics for which he is responsible to avoid being penalized by the utility. So this was basically theoretically developed by Dr. K. Srinivasan at Hydro-Quebec Research Institute, the technique he developed more than 20 years ago. And what is the basic principle? Basic principle, you see, source voltage is non-sinusoidal like this at PCC, and particular customer has non-linear load and he wants to draw this kind of current. So everything is distorted here. So what he did, Dr. K. Srinivasan did, that suppose this is the voltage at PCC. So you do the Fourier series analysis, you find the fundamental component and the dominant harmonics. Suppose there are harmonics, fifth harmonic, seventh harmonic, suppose fifth harmonic is 10%, seventh harmonic is 20%, those things. So what he did, this is the load current. So find the fundamental component of the load current and add the same harmonics in the same percentage in this fundamental component of the load current, same percentage, so that this current should look almost like this. So although there are so many harmonics here, but this is the conforming current. This is not the responsibility of the customer, because load voltage is like this. If you put a resistive load, this kind of current will be drawn by the resistive load. So this is not the responsibility of the customer. Now the difference between the two, this is the non-conforming current. So the customer should compensate only for this harmonic. So this is what we did. We did some simulation and we did some implementation also. Suppose there is a pure resistive load and voltage is like this. Okay, so the current drawn by that customer which is having pure resistive load, its current will be the same as the voltage, right? Voltage divided by current, the resistance, voltage divided by resistance. So same type of current will be drawn. So the conforming current is this, exactly same, and non-conforming current is this. It means this is not the responsibility of the customer, even if it is more than 5% TSD or whatever it is. So if this is the voltage at PCC and there is a diode bridge RL load, so it will give this type of current. So you calculate the fundamental of this, add fifth, seventh, whatever harmonics are in percentage here, with the same percentage you add here. So it will give you same type of profile for the current, which is a conforming current, and the difference between the two is this. This is non-conforming current, so the customer should supply for this current. So this is what we generated. The conforming current may become the reference current for the source. Like we discussed so many techniques, like whatever technique you use, you generate the reference source current is this, which is already distorted, but this is not the responsibility of the client. So we did, and then your reference, the source current should follow the reference source current. So THD of source current is 9.6% in this case, and before filtering it was 26.39% THD, which is now reduced to 9.6%. So that is fine. It is, even if it is more than 5% THD, this is not the responsibility of the client. So this is what actually the technique was developed. So in summary, for shunt active power filters offer best retrofit solution for all current based power quality problem. PWM based voltage source converter are preferred compared to current source converter to realize this shunt active power filter because of low cost, low size, reduced size, light in weight and reduced losses. Then there are in the notes you will find some numerical problems which you can see and try to do, and then there is a list of references here. Okay. Now coming to the other topic, active series compensation. So what we will discuss here, requirements and application of active series field compensators, configuration of active series compensator, control, and then unified power quality conditioner, UPQC, to protect a sensitive load on a polluted distribution network, a review of hybrid filters for power quality improvement, and then some numerical examples are here. So if you see voltage based power quality problem in distribution system, you may have the voltage sag, swell, voltage unbalance, flicker, transient, notches, fluctuations, waveform distortion, harmonics. There are so many voltage based power quality problem in the distribution network, and solution is the active series compensators or DVRs, dynamic voltage regulators, also sometimes you can say, a solid state synchronous series compensators. They inject the equal and opposite voltage of disturbances in series synchronous with AC mains to protect and to provide clean regulated voltage waveform across the critical load. So this is what the objective of active series compensator, that your distribution supply system may be polluted, voltage may be polluted, but you have to protect your sensitive load. On the sensitive load, you should have a regulated sinusoidal AC voltage. This is what is the objective. This is also now a mature technology to eliminate voltage spikes, voltage sag, swell, notches, harmonic, terminal voltage. So this is already being used. And there's a lot of development has taken place in varying different configuration. There are so many advanced control strategies, the same strategies which we have seen in shunt filter. You can apply, for there we were calculating reference source voltage. Here we will calculate the reference load voltage. We can calculate, otherwise algorithm remains the same, right? Solid state devices, so much development, improved sensor technology, Hall effect, microelectronics revolution, those things has accelerated the development of active series filter. Classification of active series compensation, the same type as we saw in shunt filter, converter type, topology based, number of phases based, the same type of classification we saw for shunt active filter using current source converter, voltage source converter, topology based, half bridge, full bridge, transformerless, number of phases, 2 wire single phase, 3 wire 3 phase, 4 wire 3 phase systems. So if you see the converter based classification, you see you are injecting the voltage in series with the line. This is AC male, this is single phase DVR. So this is current source converter base. As you can see, diodes are connected in series with the IGBTs, and on the DC bus you have an inductor. So current source converter are considered sufficiently reliable but have high losses and require high value of inductor and parallel AC capacitors. They cannot be used in multi-level or multi-step modes to improve performance in higher rating. So this is one type using current source converter. Voltage source converter base, see the same type of topology. On DC link you have a capacitor here. So this is capacitor based DVR, right? And you are injecting the voltage here. So VSC based, voltage source converter based DVR, they are lighter, cheaper and expandable to multi-level, multi-step versions. Like in current source converter you cannot do this, but you can do it in voltage source converter to enhance the performance with lower switching frequencies. It is more popular in UPS based applications. Topology based classification, half bridge topology, see half bridge midpoint capacitor you can take, and here you are injecting the voltage. Full bridge topology, you have full bridge topology, you are injecting voltage. So you see this is AC mains, perhaps this may be polluted like this, but you want at critical load perfect sinusoidal voltage. So that's why you are injecting voltage in such a fashion that this polluted voltage may be compensated, and on the critical load here you have sinusoidal constant, so you can see voltage. 3-phase 3-wire DVR, see 3-phase and 3-wire, you don't have neutral here, so in each phase you are phase A, phase B, phase C, you are injecting the voltage. Supply system based, so basically it is the same, just this is how you can classify, otherwise it is the same 2-wire DVS, this is using current source converter, right? And then 2-wire voltage source converter, 3-wire DVR topologies, 3-phase 3-wire DVRs. There are 3 types: rectifier supported, battery supported, and capacitor supported. So capacitor, rectifier supported, left shunt, right shunt, and then you have single phase VSC, 3-leg VSC, 2-leg VSC, and right shunt, the same thing. Okay, battery supported, you have 3 single phase voltage source converter, 3-leg converter, 2-leg converter, basically the same type of topology with capacitor supported also. Control of DVR, again the same kind of algorithm which are used everywhere. Like in power electronic devices you have shunt capacitor, so same thing. Only thing is that in shunt capacitor you calculate the reference source current, and with this you calculate reference load current. That's the only difference. Okay, so performance of synchronous frame theory based BSS supported. So just to give an example, see this is the source voltage, and here you have voltage sag, and here you have voltage swell. But your series compensator active filter is working in such a way that your load voltage is constant sinusoidal. See, it is not affected by the polluted source voltage. Load voltage is always constant sinusoidal. Why? Because when there is a voltage sag, your series compensator in injecting the voltage in phase with this voltage so that voltage at the load remains constant. Similarly, and if it is nice, then you have little injection. But if there is a swell here, then the voltage injected by your series compensator is in phase opposition with this. So here you can see source voltage is going like this, but somehow your series compensator is trying to maintain the voltage. See, this is the source voltage going like this, and this is the source current. This is the reference load voltage, and this is VDC. Here again the same thing. You have harmonics injected, so your source voltage is polluted, so your compensator is working in such a way that this does not reach to the load. So you see the load voltage is constant sinusoidal. Then the performance of SRF is the same thing, TSD. You can see this is A is what? PCC voltage. This is PCC voltage which is polluted, and it has TSD 6.34. This is the source current, which is TSD 1.02, and this is the load voltage. See, TSD is 0.65. So source voltage is polluted, but the voltage across the load has low TSD. Harmonics are almost negligible. Again, with the compensation, these things, similar type of results with different configuration. In a dynamic voltage restorer DVR system, the choice between a capacitor based, because we saw in the classification there are capacitor based DVRs and battery based DVRs, that depends on the application specific requirement such as response speed, duration of backup, maintenance needs. So if you compare capacitor based and battery based DVRs, so energy storage in capacitor based DVR, you have DC link capacitor bank, right? In battery based DVR, you have battery backup, right? Sag duration capability, that is very important for how long you have sag. But if you have a capacitor based DVR, it may be good for short sags, because after all in capacitor how much energy you can, a few cycles to a few hundred RMS, limited by capacitor size and allowed DC link voltage drop. While battery based DVRs, long and deep sags and short interruptions are possible, hundreds of RMS, limited mainly by the battery energy. Depth of how much sag is there. So capacitor based DVR, effective for moderate sags and rated load. Long deep sags require very large capacitance, so that may be costly thing, right? And battery based DVRs, they can support deep sags and temporary supply loss if the battery is properly sized. Dynamic response, capacitor based DVR, they are very fast, while battery based DVR, they are also fast, but they are not that fast as the capacitor based. Hardware complexity, it is lower in capacitor based DVR, but if you have battery based DVR, it is higher complexity, because you need battery management system and those things. Maintenance and lifetime, it depends on the capacitor health. If it is not heated up, so that life is shorter, so this is what the main concern, but there is no electrochemical aging in it. While in battery you have electrochemical which may age, So periodic replacement of fluid, thermal management, BMS, higher life cycle efforts. And then footprints and typical, so these are the things. Now coming to unified power quality conditioner. Actually, many years ago, we did a project. There was one customer in the north of Quebec which was making electronic equipment, and just near to him there was one this wood cutting factory was there. They were having big machines, induction machine to cut wood and process wood. So there was so much perturbation on the distribution network. So that customer which was making electronic equipment, it complained to Hydro-Quebec, how should I manage when there is so much perturbation on the distribution network. So Hydro-Quebec was looking for the solution. So one researcher at Hydro-Quebec Research Institute contacted me to what we can do. So this is how this project came into. Okay, we said, okay, because they have already tried DVR and other automatic voltage regulator, and those were not functioning. So we suggested, okay, when you have already tried those things, let us try UPQC. So this is how this project started. So we did this UPQC project, and you can see what is basically unified power quality conditioner. There are two inverters or converters, shunt and series. Why it is series? Because the output it is injecting the voltage in series with the distribution line, and this is in shunt, and it was so see the major function. So what is the function of this series compensator? To take care of voltage sag, if there is some voltage sag here or voltage swell. So objective was to protect that electric equipment making company, to protect so that they don't have much perturbation. They should have constant sinusoidal voltage at the entry of the plant. So our objective was to have constant sinusoidal load voltages, while the source voltages are polluted with voltage sag, swell, voltage harmonics may also be there, voltage unbalance may be there here on the source, voltage flicker, and this was, so this all those voltage related problems were taken care of by the series compensator, and the shunt compensator was taking care of current harmonics, because your load might be producing current harmonics. So we should not pollute the network. So harmonic compensation, reactive power, okay, current unbalance, neutral current, and VDC regulation. So these are all the responsibilities of this compensator. So this is what actually, and in between the two, there's a DC link and the capacitor is there. So this is what unified power quality conditioner. Now UPQC you can classify based on configurations, whether it is right shunt or left shunt, or converter topology, as we have already seen. Either you are using voltage source inverter or current source inverter, though in our case we use voltage source inverter. Number of phases, 2 wire, 3 wire, 4 wire. So we did for 3 wire and 4 wire for both. And then control strategy, same type of control strategy which we have already seen. So all these control theories, and then UPQC configuration. If you see, this is the series compensator and this is the shunt compensator. So right shunt UPQC. if your series compensator here and shunt compensator here, so left shunt UPQC. Most of the time I have seen we use right shunt UPQC, and left shunt topology is generally used for UPFC, Unified Power Flow Controller, for big power transmission lines, those things. Although UPFC, it costs a lot, in maybe in $1 billion, because there are not many places. But as I know, there are 2 in China, large size, very costly UPFCs, Unified Power Flow Controller, and there is one in USA also, I think. So not many, not at many places it has been implemented, because it costs a lot and too much engineering and complications, those things. But UPQC is still used. So this was the Hydro-Quebec network. Okay, so you see, this was the plant which we had to protect using UPQC. This is the transformer at the entry of the plant, and this is the source. And what is this plant? So this is actually, all this portion was given, simulation was given to us by Hydro-Quebec. The researchers working at Research Institute, he already simulated the network before, so he provided us with all this 6,000 MVA, this thing, 14 MVA load here, you see, star double delta transformer, and then 3 megawatt load with the 5 kilometer feeder. So this is actually the actual load, the actual network near the plant they had simulated already. Okay, so like 20 megawatt load for, so different types of loads and different types of transformer. And our work was to do work here, to do some simulation and experimental work here. So control, you see, unit vector template generation, the same thing which we did for shunt active filter, it is applicable here also. So this is what we did. Now we just saw this for shunt active filter, right? Reference voltage signal generation. So how you are generating reference voltage signal? So this is the supply voltage, phase A, phase B and phase C. You divide it by Vm. So same thing, Vm sin omega t, Vm sin omega t minus 120, Vm sin omega t plus 120 divided by Vm. So it will be unit vector left, USA, USB, USCC, UA sin omega t, UB sin omega t minus 120, UC sin omega t plus 120, right? So you have unit vector, then you use PLL to get sin omega t cos omega t terms, choose sin omega t. So you see, you have UA, UB, UC, and you multiplied it with the peak value, whatever the desired amplitude of voltage you want at the plant terminal, at the entry of plant. Okay, so VLA, so VLA is VLM multiplied by this unit vector. So this is the same way VLB, VLC references you can calculate, and then the same thing basically what you do in active filter, you compare it with the actual voltage at the load, and then you generate the signal for your inverters. See, source for source current for shunt active filter, the same thing which we do for shunt active filter, we have already seen the same thing. Okay. So these are some of the simulation results with UPQC. This is the source voltage, this is load voltage, this is injected voltage, this is VDC, this is source current, this is load current, and this is the shunt compensator current. So you see, this is the source voltage, and your load current is like this. This is the load current, which has 27.6 THD, this load current. So till now your shunt active filter is not on. So in UPQSC, what is important, you have to first start your shunt active filter so that it will keep the voltage as VDC constant. That is very important. Okay, so here we are starting the shunt compensator. So you see, VDC was at certain value, then it comes to their required value VDC, and here you can see the active component of the current, basically it is charging the capacitor. So that's why you see the fundamental component of this also. Okay, so VDC is charged to the required value. So as soon as you have started your shunt compensation, it has started working its work. What work is it? To compensate for load current harmonics, right? So the load current is like this, but the source current is like this. Why initially the source current is high? Because shunt active filter is charging the capacitor, so it is taking extra current from the source. So this current is extra, otherwise it becomes constant here. Till now you have not injected any voltage, so series compensator is not working here because there is no requirement of series, because otherwise the source voltage is constant sinusoidal. The only problem was the non-linear load, so your shunt active filter is able to take care of that situation. Okay, so you can see the but here there is some change of load, so it is adjusting to this. So THD after compensation, so source current THD after compensation 4.33%. Now coming to the power factor correction. So you see, this is the source voltage, this is the load voltage, this is injected voltage. So for power factor correction also you don't need the intervention of series compensator. VDC, source current, load current, and shunt current. So until now, you see, here you are starting your shunt compensator, and before that you can notice that the source current is lagging behind the source voltage. So that is why power factor was 0.61. Okay, the source voltage, if you see, there is a angle here. Source current is lagging behind. Now our objective is to have improved power factor. So when we start our shunt compensator, see, the source current changes like this, and here you can notice now the source current is in the same phase at the source voltage. Okay, while the load current, you see, the load current is lagging behind, but the source current is in phase, so the power factor becomes 0.98. So shunt active filter is able to take care of the power factor condition. Although we have not done anything, only thing is that we are calculating reference source current, and your shunt active filter is following that principle and automatically is taking care of this thing. Now voltage harmonic compensation, this is the source voltage, and you can see it is polluted, it is not sinusoidal. So the load voltage is also the same. This is the injected voltage, this is VDC, this is source current, this is load current, and this is the compensator current. So your shunt compensation. First you have to start your shunt compensation. So as soon as you start your shunt compensation, it charges the DC capacitor at DC link, is charging. Okay, and at the same time you can see the source current initially large, but then it subsidizes and it is sinusoidal because all the harmonics, all the load harmonics are being compensated by the shunt active filter, and your source current is already sinusoidal now. All the current harmonics are taken care of. Once you have started sorry, something क्या किया? ओके, ठीक, थैंक यू. ठीक है, ठीक है. Okay, so you see, your VDC is constant at the reference value, and now once you have taken care of your load current harmonics, then you start at this point your series compensator. So as soon as you are starting series compensator, this is the voltage being injected by the series active filter, so that your load voltage becomes sinusoidal, while the source voltage is still polluted, but the load voltage across the load, sensitive load, is constant. So this is how. Okay, so the load voltage TSD now is 4.7, and before compensation here it was 19.2%. ठीक? हाँ भाई, so let us see the voltage sag compensation. Okay, this is the source voltage. So you see, source voltage is there. This is the load current. So we are starting our shunt compensator here. So before starting shunt compensator, your source current is same as the load current. But once you have started your shunt compensator, it is charging your DC link voltage to bring to the reference value, and so extra current initially for 2-3 cycles. Then your source current is perfectly sinusoidal because your shunt compensator, in compensating for harmonics, your source current is sinusoidal here. Now you have started your series compensator. Series compensator is started here. Till now there was no voltage sag. See here, there is no voltage sag. But as soon as the sag starts, your series compensator starts working and it is injecting the voltage in phase with the source voltage. See it? Oh. In phase with the source voltage, so that the load voltage does not feel the voltage sag here, and the voltage here at the load is constant sinusoidal. Although you can see that some fundamental component of current is here, because all the time this shunt compensator has to keep charging your DC link voltage capacitor. Voltage swell compensation, same way. See, until you start your shunt compensator, your source current is polluted. Once you have started DC link, this I have already repeated, and the source current becomes sinusoidal. Okay, here everything is fine in source voltage, so load voltage is also fine. But at this point, there is a swell. So although you have started your series compensator here, but it does not react. But as soon as it senses the voltage swell, it started injecting the voltage in phase opposition. See, this one is in phase opposition of this. Phase opposition of this. So that the voltage across the load is constant sinusoidal. These are some experimental results. This is the source voltage. This is the source current. This is the load current. See, load current is lagging behind the source voltage because load is perhaps the inductive load. So load current is lagging behind. But since you have injected the shunt current in leading, see, this is leading shunt current. So that's why your source current is in phase with the source voltage. So harmonic compensation, this is the source voltage and this is the load voltage. Perhaps series compensator has taken care of, so load voltage is sinusoidal. This is the load current, but this is the source current. You can see it is perfectly sinusoidal. And this is for the load change. Load is changing here, so it is taking care of that thing. Performance of UPQC with voltage sag, these are the experimental results. So here you can see in comparison to this, there is a voltage sag here. This is the source voltage. So your series compensator is injecting the voltage in phase with the source voltage so that the load voltage remains constant. This is for voltage swell. So here you can see the voltage, source voltage is large. So your series compensator has injected the voltage in phase opposition to source. Let us see how. Can you see this? This way, and you see this is in phase opposition. It has injected the voltage. Your series compensator has injected the voltage in phase opposition to this so that voltage across the load remains constant, sinusoidal. Then for neutral 4 lag for the neutral current, you add this one. So this is the source voltage. You see, highly unbalanced non-linear load currents. In all the 3 phases, different types of currents and non-linear unbalanced currents. But the source currents are perfectly sinusoidal balanced. And the shunt filter, active shunt filter in all the 3 phases providing different types of compensating shunt current to make the source current perfectly sinusoidal for this type of load, because all the 3 currents here, load currents are different while the source currents are same. So different types of shunt filter currents are injected. So if you see the current unbalance factor, like we saw the voltage unbalance factor also, the same equation we can use for current unbalance factor. Maximum of average current to minus IA or minus IB or minus IC divided by the average current. This is what we did for voltage unbalance also, right, in the first lecture. The same equation we can use for the current also. Before compensation, ISA, ISB, ISC, RMS values are very different and peak values are different. Okay, so, and THD, see, different THDs for all the 3 phases, and this is the K factor, and this is the power factor you can see. So load current unbalance factor was 45.76%. After compensation, ISA, ISB, ISC RMS values are almost equal. Peak values are almost equal. TSD much less than 5%. K factor is almost 1. Power factor is almost unity. So current unbalance factor become 1.08. So this is what is the function of UPQC. So this was a very nice project. Now, if you see, a lot of work is going on hybrid filters. Okay, why hybrid filters? There are some problems related with passive filters, because classically you use passive filters for filtering harmonics. So if you are using passive filters, what are the problems? It has the fixed compensation, because once you have put inductor, capacitor and other thing, it is fixed. It is not a software that you can change it every day. It is hardware, so it is connected with the network. So it has the fixed compensation. And if the network changes, load changes, then there is a possibility of resonance, because now the same inductor, capacitor, those things, passive filter may not be tuned properly for that load and network condition. So there is a possibility of resonance. And moreover, it has a large size conductor, inductor and capacitor, etc. But everything is not good with active filters also. There are problems with active filters also. Sometimes the size of active filter may be up to 80% of the load in certain application. There are certain kind of very highly nonlinear loads. They may require higher compensation. Okay. One active filter may not compensate for voltage and current. We already know this thing, that okay, for current problems we use shunt filter, for high voltage problems we use series compensator. Cost of filtering may be large, therefore clients may hesitate to use active filters. So this is the thing, it depends how big is the load and those things. So I don't know what is the cost of active filter nowadays here, maybe still, but one of my student has a company, he makes this active filters here in Mumbai, and he is selling good, so it should be a good business, because we have a lot of, in India we have a lot of power quality problems. However, in Canada we don't have much power quality problems, so there is not much market of active filters in Canada and US, those places. So the cost may be a factor, because I visited, as I was telling you 20 years ago, I visited a Bombardier factory which makes aeroplanes. They have their drives labs. It was very polluted, so they calculated it will cost $10 million to put an active filter produced by ABB at that time 20 years ago. So the Hydro-Quebec said, you are polluting our network, so anyway we will give you 20% discount. So $20 million were paid by Hydro-Quebec to Bombardier and $8 million by Bombardier to improve the situation. So it may be a costly thing, right? Therefore, a hybrid filter may be a good choice to reduce the cost and to improve the performance. So that's why a lot of work is going on with hybrid filters. If you see the classification of hybrid filters, you have single phase, 3-phase 3-wire, 3-phase 4-wire system. Same thing for single phase, passive, 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 active, active, active. So these three combination. Same thing for 3-phase 3-wire, passive, 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 active, and active, active. And 3-phase 4-wire, passive, 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 active, and active, active. There's some error, you can connect it. So there are total 156 configurations in these are 9 categories. In these 9 categories, 156 configurations, and I have seen in last 20 years, almost all the configurations are used by engineers around the world. Okay. So combination of 2 passive elements. There are 2 possibilities, this possibility and this possibility. You have series passive filter and you have shunt passive filter on the right side. But here you have shunt passive filter on the left side, and here you have shunt passive filter, series filter here, series passive filter. So it may look simple. This passive filter, you say, okay, one leg is there, but it is not like this. When you are having a non-linear load, you have 5th harmonic, you have 7th harmonic, 11, 13, so many harmonics are there. So many times you will have to use passive filter for 5th harmonic, another leg of passive filter for the 7th harmonic. Then you may use high pass filter for the 3rd, so at least you have 3 legs minimum here. Like if you see, there is one high HVDC transmission line in the north of Canada, north of Quebec. There is a Bay James power plant which generate more than 5,000 megawatt of hydropower electricity. And then the energy is transported by DC line. So they have HVDC system there. So in that HVDC system, they have 2 6-pulse converters in series. So it means 5th, 7th harmonic are gone, so it will remains 11th and 13th harmonic remains, and perhaps 17, 19 may have gone, then 23rd and 25th harmonic. So you have basically, they have basically 4 passive filters, one for 11th, 13th, and I think for 23 and 25th harmonic they have 4, and then one passive, one high pass filter. So they have 5 legs of filter. So sometimes it may be very involving and technically difficult. Okay, so so these are combination of 2 passive elements, 2 possibilities. Combination of 3 passive element. So this is a type of T connection, and this is a kind of pi connection. So these kinds are also being used, 2 possibilities. Combination of 1 passive and 1 active element. There are 8 possibilities. Okay, 1 passive, 1 active, series active filter. So still people use this thing, okay? And they are in series. If they are connected in shunt, it is like this. If they are passive filter is here and active filter is here. And you see active filter here and passive filter is here. So some of the, for example, this is very popular topology, which is very used a lot. So what this series filter does, it forces the harmonics to go to this passive filter to not to pollute the network. So 8 possibilities are there. So these are 4 possibilities, and another 4 possibilities are there. This is also very popular topology. This is called harmonic isolator. This is also a very popular, and I have seen many research articles on this topology also. So 2 passive and 1 active, if you use, there are total 18 combinations. 2 active and 1 passive, there are total another 18 possible combinations. Combination of 1 active shunt and 1 active series filter, there are 2 possibilities. 1 active shunt and 1 active series. So this is what? UPQC. Yeah, just we saw UPQC. This is the topology, right? And 1 active shunt here on the left side, and right side you have this series filter. So this is UPFC. Combination of 3 active filters, there are 2 possibilities, like this pi type, no, this T type, and this is pi type. In general, we don't use hybrid filters with more than 3 elements. In total, there are 52 combinations. All these combinations are valid for single phase, 2-wire, 3-phase, 3-wire, and 3-phase, 4-wire system. So 52 multiplied by 3, so 156 combinations are this, and they are really used. This is not just theoretically, people use those combinations. Now, selection criteria for hybrid filters. It will depend type of supply system. It is single phase, 3-phase, 3-wire, 3-phase, 4-wire. We have seen all those topologies. Nature of load, whether it is current based or voltage based, load capacity. So if it is less load, then the topology will be different. If it is high loads, then you have to change we have seen the topologies. Current compensation required, or you require the voltage compensation, so topology will change accordingly. Pattern of load, whether it is fixed, variable, fluctuating, level of compensation required, okay, and then cost, size, weight, efficiency, reliability. So there are so many factors, environmental factors. So, so there are so many possibilities. What are the latest trends and future development? Development of new topologies. Reduced rating of AF element allows the use of switching devices which operate at very high switching frequencies, providing fast response, reduction in size of repulse filter, passive filter, and size of DC bus capacitor. Development, so this is what is latest trend. Development of improved control algorithm. Okay, like sensorless control. If you use sensorless control, you don't have to use certain sensors, right? You can save on this. Development of improved switching devices like gallium nitride and silicon carbide. Application specific integrated circuit and integrated power module. So a lot of work is now from silicon based devices, IGBT. We are moving towards gallium nitride or silicon carbide because they work on high frequency. Switching losses are less, conduction losses are less, resistance, online resistance is very less, so less losses in gallium nitride as well as in silicon carbide. And efficiency may be as high as 99% efficiency with those devices. And switching frequency is very high, like for silicon carbide, I don't know, maybe from 10 kilohertz to 200 kilohertz, you may go to switching frequency. But for gallium nitride, it may be 100 kilohertz to 1 megahertz. The frequency may go, switching frequency up to, and in certain, in telecommunication, other area, I have seen that sometime it may go to 5 megahertz switching frequency. So see, the miniaturization of the electronic is being led by this gallium nitride, but they have their own problem, but they are for low voltage, low power application. I think up to 650 volt you can go gallium nitride devices, while silicon carbide may go up to 1200, more than 1200 volt or so. So silicon carbide devices, they may be for high power application, high voltage application, those. Like one of my postdoc who did postdoc with me more than 25 years ago, Dr. Brij Singh, he did PhD with Professor Bhim Singh, I think in 97, then from 98 to 91 he was with me as a postdoctoral fellow more than 25 years ago. Now he is a big boss in John Deere company. You know, there is a John Deere company in North Dakota, US, United States. They make big size tractors, dumpers, forestry, agriculture equipment. Very, very big size. So what he's there for last almost 18, 19 years, and now he is the chief of power electronic department in John Deere. So what he is doing, when President Obama was there, he got $140 million grant $140 million grant he got to work on silicon carbide devices. And then he developed, he has already converted many big size dumpers and forestry equipment in electrification of those big machines, which are in megawatt. They have synchronous PMS, SEM in megawatt range. Those are big machines. They move and they cut the forest and do all kinds of, and in agriculture also. So this is what his work is. He is using silicon carbide. He has converted all that equipment using diesel or petrol based those machinery to electrification he has done. So when he got this $140 million grant, President Obama invited him at White House for dinner. So it was really a good thing to see. So a lot of work is going on, gallium nitride and silicon carbide and people, but they have their limitations and those things. Development in magnetics to reduce the losses. Lot of development is going in magnetics. Losses, size of passive filters such as transformer and inductor. Development in supercapacitor technology. Energy storage devices, systems. So much work is going on. You are already using lithium ion and those things. But I was in China for 3 weeks. In September, I was in China and I visited many universities and industries in China. So, and then I attended one conference organized by one company. And there were, so I was also a panelist and I also presented something. But some panelists, and they were saying that there is a problem with lithium-ion battery now. In China, for electric vehicle application and other places, lithium-ion battery perhaps is not stable and sometimes it catches fire. So some fires were very deadly. So this is the problem with lithium-ion battery. So what happened, when I attended that a small one-day conference organized by one company there. So they were talking about the energy storage. It is not related with active filter, but they were talking about large size energy storage. So how there are many possibilities how you do energy storage to make the grid stable, because there is a very serious, I will tell you, there is a very serious problem going on in China, and that is the voltage instability in power system. And that voltage instability is instigated by the variation in renewable energy integration. So I will tell you, when I come to renewable energy integration, I will tell you what is the problem, what is going on. Okay, so that's it. And then there are here, you see some numerical example based on active compensation. So you can see here and read. It may give you some idea, and then there are list of references here. Okay, that's it for today. Right time. Is there any question? How to close it? Is there any question related with active filters or something? So many people. जी? Yeah. Yeah, this is the problem. That's why you can use PLL basically. Although you measure the VSA, VSB, VSC, but you take it through PLL so that it gives the sinusoidal template. Yeah, this is a very good question. Yeah, this is what actually we felt, because we worked on this topology, this control algorithm more than 25 years ago. Actually, this is Dr. Brij Singh. He developed some technique on unit template, and we have many research articles with him. And at that time, we compared different things, And that was the cheapest way at the time. Okay, don't use PLL, we can just measure and the base. But if the supply voltage is polluted, then your unit template will also be polluted. Yeah, that's the problem there. Then you have to go through PLL. PLL is available in math labs and those things. Yeah. Okay, that's it for today. Thank you very much. How to close this thing?